Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate playlist. In today's video we are going to discuss factors that are affecting temperature changes in the atmosphere. And while this video is tailored to the atmosphere and the air, it really applies to any system out there. Today's video builds heavily on the topics that we discussed in chapter 2 of this playlist. And in that chapter 2, you will remember we define net radiation, which is the difference between shortwave radiation, predominantly radiation from the sun, and long-wave radiation, predominantly terrestrial radiation. And this net radiation, which can be positive or negative, is redistributed through the next three fluxes. And these are QH, which we call sensible heat flux, plus QE, which we call latent heat flux, and plus QG, which we call ground heat flux. The heat flux that is causing temperature differences is the sensible heat flux. And therefore it is called sensible heat flux because we can sense it. Change of this flux, change of sensible heat flux is resulting in temperature changes. If this flux is increasing, we feel it as warmth, we feel it as increase of temperature. If this flux is decreasing, we feel it as the drop of temperature. But just looking into this equation, you can see that this flux will depend on other three fluxes. In other words, if we have net radiation, whether it's positive or negative, then this value will be redistributed among these three fluxes. If it is redistributed in a way that it mostly goes into QH, then there will be big temperature differences associated with this net radiation. However, if this Q star is redistributed mostly to latent or ground heat fluxes, then less will go to QH and there will be smaller temperature variation associated with the same net radiative flux. So now let us qualitatively discuss what are the parameters that are controlling these four terms. If we go to Q star, then what is controlling net radiation on this planet is of course seasons. Less flux in the winter season, more in the summer season. Then day cycle, or I can write here day-night. During night there is no sun, no shortwave radiation. During day we have solar radiation. Another is terrain characteristics, slope of the terrain, type of the soil or type of the terrain or so on. We know that white surfaces like this snow outside that I'm looking through the window in Montreal are reflecting solar radiation. For example, snow reflects a lot of shortwave radiation, fresh snow up to 90%, as we studied in chapter 2. But at the same time, snow is very good absorber of infrared radiation. So you see it therefore affects in a complex rather way this Q star. Another factor that is affecting Q star is clouds. And I could say also humidity. First, clouds. Clouds are again white objects. They reflect a lot of incoming solar radiation. But clouds are also very good absorbers and emitters of long-wave radiation. Humidity, amount of water vapor in the atmosphere predominantly affects long-wave radiation because water vapor is very good absorber of long-wave radiation. And lastly, elevation. Higher higher elevations, mountains can receive more shortwave radiation. And you also know that if you climb on top of some mountain, you have to wear sun protection because you can get sunburns. More solar radiation is reaching mountain tops. But elevation is also directly affecting temperature through vertical motions in the atmosphere, as we will study in one of the next videos. Now, Seasons is something that we will study in chapter 3. Daytime variations is something that we will study in chapter 3, although we touched upon day-night variations, already in chapter 2. Terrain influences will be studied here, as well as elevation. Clouds and humidity will be separate chapters because of their enormous importance in atmospheric sciences. Now, QH, or sensible heat flux, which basically the lecture is all about, is also directly influenced by several factors. The biggest factor is temperature difference, which I will abbreviate T-diff. Temperature difference between the air and surface, and you know we use FWC for surface. So temperature difference between, let's put between. Temperature difference between air and the surface. Namely, the bigger the temperature difference, the bigger the heat flux. Then heat flux sensible heat flux will also be affected by wind. If we have windy weather, then there will be a lot of mixing between different elevations in the atmosphere, and that significantly redistributes this sensible heat flux and therefore affects temperature. And lastly is atmospheric stability. Atmospheric stability, which is extremely important concept in atmospheric sciences, which I will discuss in great details in next chapters. But atmospheric stability, in simple words, describes tendency of the atmosphere to amplify, suppress, or be neutral to vertical motions. If the atmosphere is suppressing vertical motions, we would say it is stable. If the atmosphere is indifferent to vertical motions, we would say it is neutral. And if the atmosphere is amplifying vertical motions or supporting them, we would say it is unstable. And as you can see, therefore, this also affects the level of mixing across different altitudes in the atmosphere, and therefore that affects the redistribution of this flux. And therefore it affects temperature changes. Then the next flux is QE, latent heat flux. And latent heat flux is affected by typically soil characteristics, and particularly soil moisture. If the soil is very moist, in extreme case, if it is water, such as ocean, seas, lakes, rivers, then there is great potential for evaporation, and this flux can be increased. If the soil is very dry, such as certain desert regions, then this flux is very small, and we have something in between for soils that are between these two extremes. For example, forests and agricultural areas can have quite large QE, because there is a lot of so-called evapotranspiration, which is evaporation from the plants. But this flux also is affected by humidity in the atmosphere. And of course, if the atmosphere is very humid, then the flux is smaller than if the atmosphere is very dry. But if the atmosphere is very humid, there is a very large potential maybe, for condensation, which again will affect this flux. The next flux here is QG, flux to the deeper layers of the ground, and this one is particularly affected by soil characteristics, let's say properties. If the thermal conductivity of soil is very high, then this flux will be large, as we studied in chapter 2 in the lecture on conduction of heat. If the soil is very poor conductor of heat, then this will be very small. And there is one more term that is not listed in these equations, and that can affect temperature changes over a point in the atmosphere, and that is advection. And advection is defined in chapter 2 of this playlist. Advection is transport of some quantity due to wind. In this case, we are talking about transport of heat by wind. So that means if there is temperature difference between two regions and we have wind blowing from one region to another, there will be advection of heat from one region to another. This also means if we do have two regions and there is wind blowing between, but they are sitting at the same temperature, there will be no advection of heat. And at the same time, of course, if there is temperature difference between two regions, but there is no wind, again, there will be no advection. So advection depends on temperature differences, but not between air and the surface, but temperature differences between two locations and wind. And the larger the wind speed and the larger the temperature difference between two locations, the larger the advection. Lastly, there is one more term that I purposely omitted, rather factor in Q star, which is not often listed, but for completeness we should list it, and that's solar activity. Namely, of course, if the sun all of a sudden becomes much more active, then this Q star could change significantly, particularly shortwave radiation. But solar activity is pretty constant when compared to all these other factors, so quite often it is just assumed as a constant. But it is not, so we should know it is not exactly constant. At any rate, I talked about solar activity in great details in chapter 2, so it will not be covered in this chapter. But in this chapter we will mostly talk about temperature differences associated with Q star and Q age, and these other processes will be discussed in next chapter because humidity and moisture is such an important property of the atmosphere that it deserves its own chapter in this playlist. In the next video we are going to talk about seasons and what is causing seasons on this planet. Until then, please make sure to like and subscribe, share this video with your friends and family, and until next video, goodbye.